Welcome to this session on continuous tank reactor or CSTRs, which are one of the most fundamental types of reactors used in chemical engineering. A CSTR is a reactor where reactants are continuously fed into the system and products are continuously removed. This allows the reactor to maintain a steady state operation under ideal conditions. What makes CSTR special is the assumption of perfect mixing. This ensures that the contents are uniform in temperature and concentration at any given time. This simplification helps us model and predict reactor performance mathematically. They are widely used in industries like chemical and polymer manufacturing, where control and consistency are key. Now, why should we study CSTR modeling? Modeling helps us to understand the dynamic behavior of reactors. It detects mismatches between the plant and the model, which is crucial for the fault detection. It also aids in control strategies, optimization, and ensures safe operation by predicting how the reactor will respond to changes. Now, let's take a closer look at the schematic of a CSTR. This is a jacketed reactor, meaning it has a surrounding jacket through which a cooling or heating fluid can flow. The feed enters the reactor at a flow rate Fi with a concentration of A denoted as CAF and the temperature TF. The reactor operates at a level H and the cross-sectional area is AC. The stirrer ensures perfect mixing. The product exits the reactor at the same flow rate Fi with concentration Ca and temperature T. Jacket fluid enters at Tj in and exits at Tj. We also assume a first order irreversible reaction A to B occurs within the reactor. This diagram sets the stage for deriving mass, component and energy balances, which we will do in the upcoming slides. Make sure to remember the terms Fi, CAF, Ca, TF, T, Tj in and Tj because we will use them throughout the derivations. Before we jump into equations, let's clarify our assumptions. These simplify the real system to make the modeling manageable. Number 1. Negligible heat loss to the atmosphere, which is all heat transfer occurs only through the jacket. Number 2. Constant density ρ and heat capacity Cp, which they don't change with temperature or concentration. Number 3. Perfect mixing in both the reactor and jacket, and so the properties are uniform throughout the reactor. Number 4. Neglect thermal inertia of metal walls, which is they don't absorb or store heat. Number 5. No spatial variations in temperature, concentration or reaction rate, which is the properties are same everywhere inside. Number 6. Outlet temperature and concentration equal those inside, that is due to perfect mixing. Number 7. Constant overall heat transfer coefficient U, it simplifies the energy balance. Number 8. No separate energy balance for the jacket. Instead, the jacket temperature Tj is treated as a control variable. These assumptions helps us turn a complex system into a solvable set of equations while still giving us realistic insight into the system behavior. Now, let's derive the total continuity equation, which is essentially a mass balance over the entire reactor. The flow rate into the reactor is Fi and the flow rate out is F0. Assuming there is no reaction that changes the total mass, the rate of production is zero. According to the energy balance equation, rate of accumulation is equal to inflow minus outflow plus generation. But generation is zero here. So d rho v by dt is equal to Fi rho minus F naught rho. Now density is constant as per the assumption. So we can factor it out. Rho dV by dt is equal to rho Fi minus F naught. Cancelling rho gives dV by dt, which is equal to Fi minus F naught. So, if inflow equals overflow, the volume stays constant. Further simplifying with V equal to AC into H, we will get dV by dt is equal to AC into dH by dt, which is equal to Fi by F naught. Finally, dH by dt is equal to Fi minus F naught divided by AC. So this is our final total mass balance equation. It relates the change in liquid heat inside the tank to the difference in flow rates. Now we apply the mass balance to a specific component, say component A. Here's a general form again. Accumulation is equal to inflow minus outflow plus generation. Inflow of A is equal to Fi into CAF. Outflow of A is equal to F naught into Ca. Generation of A, since A is consumed in a first order reaction, it's negative. Minus RAV is equal to minus KCA into V. So, putting it together, dCAV by dt is equal to FICAF minus F naught Ca minus KCAV. Using the product rule, V dCA by dt plus CAdV by dt is equal to FICAF minus F naught Ca minus KCAV. If volume V is constant, dV by dt is equal to 0. So, V dCA by dt is equal to FICAF minus F naught Ca is minus KCAV. Now divide by V, which gives dCA by dt, which is equal to Fi by V into CAF minus F naught by C into Ca minus Kca. This gives us the rate of change of concentration of A in the reactor. Now for reaction rate we use Arrhenius law. RA is equal to Kca, where K is equal to K naught exponential of minus E by RT. Substituting that in, we get dCA by dt is equal to Fi by V into CAF minus Ca minus K naught exponential to the power of minus E by RT into Ca. This final form is a first order differential equation that captures how A's concentration changes with time, including flow and reaction effect. Finally, we derive the energy balance. Again, the format: accumulation is equal to in minus out plus generation minus loss. Energy input is equal to Fi into rho into Cp into Tf. Energy output is equal to F naught into rho into Cp into T. Heat added by reaction, which is equal to minus del H into Ra into V. Heat transfer via jacket is equal to U into A into Tj minus T. So, d into rho CpTV by dt is equal to Fi rho CpTF minus F naught rho CpT plus minus del H RAV plus UAJ into Tj minus T. Now apply product rule to LHS. Rho CpV into dt by dt equal to Fi rho CpTF minus F naught rho CpT plus minus del H RAV plus UAG into Tj minus T. Cancel rho Cp from all terms since it's constant. Divide through by V. So we will get an equation dt by dt is equal to Fi by V into Tf minus T plus into minus del H by rho Cp into K naught exponential of minus E by RTCA plus UAJ divided by rho Cpv into Tj minus T. This final equation tells us how the temperature evolves in the reactor. It captures the effect of incoming fluid, exothermic reaction, and heat exchange with the jacket. It's vital for designing temperature control strategies. Let's now understand the advantages and disadvantages of a continuous stirred tank reactor. Starting with the advantages. First, a CSTR maintains a uniform composition throughout the reactor because of continuous stirring. Second, it allows for easier temperature control, making it ideal for reactions sensitive to temperature changes. Third, the construction is simple and maintenance is easy, reducing overall operational challenges. Fourth, it offers flexibility in operation, allowing easy addition of reactants and removal of products. And fifth, ACSTR is highly suitable for large-scale liquid phase reactions, making it widely used in industry. Now, moving to the disadvantages, a CSTR requires a larger reactor volume to achieve the same conversion compared to a plug flow reactor. Second, it typically results in lower conversion per pass, especially for first order reactions. Third, the continuous stirring increases energy costs during operation. Fourth, for very fast reaction, a CSTR may not perform well, often requiring multiple reactors in series. And fifth, back mixing inside the reactor can lower the overall reaction efficiency. These points helps us understand why CSTRs are highly popular but also where they might not be the best choice. In conclusion, the continuous tank reactor is a versatile and widely used reactor in chemical industries. Its advantages like uniform mixing and ease of operation make it highly effective for more processes. However, its limitations such as lower conversion efficiency and higher energy costs must be considered during reactor selection. A clear understanding of these factors helps engineers choose the right reactor based on process needs and economic feasibility. I hope this video made a clear idea on the CSTR. Thank you. Have a nice day.